Hello students, in this lecture we will see experiment number 6 that entitled to determine the fiber and void fraction of a given glass fiber reinforced composite sample. Here you have to remember that these experiment numbers are according to the list that is uploaded on the LMS. First choice for any application is to choose a proper material, and whenever you think of mechanical properties, here you need a material which has high modulus and it has good ductility. This requirement is because if you use a brittle material, that will break without any warning or it will break suddenly. Suppose if you make a bridge of a brittle material, it won't give any warning before breaking and it will break down suddenly. So there may be a loss, financial loss or human loss also. That is called as catastrophic failure. So whenever you think of mechanical properties, it should have good ductility also along with high Young's modulus. That is to prevent accidental overloading. So when we have overloading, when we load the bridge more than its capacity, it will undergo plastic deformation. That is a warning sign for us. Then you can remove the load, but there won't be any failure. So what choices we have for this kind of application? We have 4 choices: metals, polymers, ceramics and covalent solids. Let's look at the properties of this one by one. So first we will see the properties of metal. Metals are generally having good ductility. They can form alloy very easily. Alloy is a mixture of more than one metal. Metals are generally easily machinable. Machinable means they can be castable, they can be moldable, they can be weldable. Metal generally have moderate Young's modulus, but the problem with metals is that they have higher density. Now why I call this as a problem? Because higher density leads to higher cost. The cost of metal depends on its weight. Higher density, higher cost and low efficiency. So we need a material which is lightweight, and polymer is the best choice here because polymers are lightweight in nature. But the problem is that they have very low Young's modulus. They cannot withstand high temperature. The melting point of polymers is generally less as compared to metals or ceramics, and they have very poor wear resistance. They can torn very easily. So we cannot use polymer also. The next obvious choice is the ceramics. Ceramics have high Young's modulus than the metal and polymers, but the problem is they are brittle in nature, and due to this brittleness they will have catastrophic failure. As I have told you in the last slide, they will fracture without any warning. So we cannot use ceramics also. The remaining option is now only the covalent solids. These solids have highest Young's modulus among all materials due to the strong bonding, but we rarely use these for any application because of the catastrophic failure. Now you can see that we cannot use metal because they are having high density. We cannot use polymer because they have low Young's modulus and low melting point. We cannot use ceramics also because they are brittle, and covalent also because they also shows catastrophic failure. So we cannot use these 4 materials type independently. Now the obvious choice is we can mix this material. If you mix this material, that we call as a composite. So composite is a mixture of 2 or more than 1 different materials, while alloys is a mixture of 2 or more than 2 metals. In composite we have 2 different material types, for example ceramics and polymers, metals and polymers. So composite can be formed by a combination of two or more material types, and in composites they don't lose their individual identity, while in alloys they can lose their individual identity. And composites are made by keeping in mind a particular application, such as enhancing the strength or efficiency or durability. Now, if we have a composite, can we use the properties of different materials? Suppose I have a metal which is having moderate Young's modulus but which is ductile in nature, and I can use a ceramic which is having high Young's modulus. If I mix these two, I will get a composite, and we can use the Young's modulus of these different materials for our purpose. So if you form a composite by addition of two different materials, we can alter or we can tune the modulus of materials. For example, titanium diboroide is added to the iron to increase the modulus of iron, because iron is ductile in nature and it has low Young's modulus as compared to TiBt. Here, so whenever I say composite, we will have two different materials. One we call as a reinforcement material. What is meant by reinforcement? That we added to the material which is having low Young's modulus, that we call as a matrix. So we have two types here. One is called as a matrix. I will write here. And another is called as a reinforcements. So here materials to be added. And matrix is host material. So composite will form by the reinforcement, that is addition into the matrix, that is a host material. And here typically the second phase means reinforcement is harder and brittle, and the ductility is provided by the matrix. So matrix is providing the ductility here, that is support to the reinforcement, and these reinforcement are generally brittle and harder in nature. So as I said, as soon as I say composite, there are two different materials. One is called as reinforcement and one is the matrix. If we add reinforcement particles or fibers into the matrix, we will get a composite. Typical matrix material are epoxy, vinyl ester, polyester and phenol formaldehyde resins. Typical reinforcement materials are glass fibers or called as fiberglass, carbon fibers, papers, wood and asbestos. Here for your reference, a carbon fiber that is shown in the black color is shown, and compared to the human hair that is shown in the grey color. There are three types of composite. One is called as laminate composite, in which we have alternate layers of reinforcement and matrix. So one is the reinforcement, another is the matrix. Reinforcement and then there is a matrix. This we call as a laminate composite. Another type is called as a fiber composite or aligned fiber composite. Here we have a fiber, those are aligned and are added into a host matrix. And third type of composite is called as particulate composite. Here we have particles or particulates of reinforcement added to the matrix. This is typical example of laminate composite. So here we have a matrix shown in the blue color, and these yellow colors are the reinforcement material. That can be glass, that can be carbon fibers. Another example is shown here. We have asbestos sheet that is added, and there is a matrix here. Align fiber composite is shown here, where we have aluminum as a host material or a matrix, and silica fibers are added into the aluminum. So aluminum is ductile in nature and silica fiber are hard in nature. If we add these two, we will get a material which is having moderate Young's modulus. So in our laboratory experiment, we will see a typical fiber reinforced plastic composite. Here we have fibers. Those are made up of glass that we call as a fiberglass, and that we have added into the matrix of epoxy. As a result of this, we will get a fiber reinforced composite which attributes to the superior properties as compared to the individual fiber and individual matrix. These fiber reinforced plastics are commonly used in aerospace, automotive, marine and construction industries, and also we can use in ballistic armors as well. So to find out the Young's modulus of a composite, we use the formula called as YC, that is Young's modulus of a composite. I will write here. Vf, that is volume fraction of fibers, Yf, that is Young's modulus of fibers, then we have Vm, that is volume fraction of matrix, and Ym, that is Young's modulus of matrix. So the Young's modulus of a composite is depend on the volume fractions of fiber and Young's modulus of fiber, and volume fraction of matrix and Young's modulus of matrix. As an example here, aluminum is a lightweight and that is ductile in nature, so it can withstand the accidental overloading. It will go under plastic deformation as soon as we apply load more than its capacity. The Young's modulus of aluminum is around 71 gigapascal, and we have a boron that is very strong, that has a covalent bonds. Here the Young's modulus is 440 gigapascal. But the problem is boron is brittle in nature, so it cannot withstand accidental overloading and it will have catastrophic failure. But if you add these two materials, we will get a composite, and the Young's modulus of composite will lie in between 71 to 440 GPa. So you can tune or you can alter the Young's modulus of composite as per your choice. So we can conclude from here that the Young's modulus is depend on the volume fractions. There are two types of volume fraction in the composite. One is called as fiber volume fraction, another is called as void volume fraction. Void is a free space between two materials. So what kind of materials we have here? One we have fibers and another will have a matrix. The gap between these two is called as a void. and that void fraction is also important parameter here, because the voids can act as a crack initiation sites. It means that crack can start from the voids and they can allow the moisture to penetrate into the composite. So voids can act as a crack initiation sites and they can allow moisture to penetrate into the composite. So we need lower void fraction. Void fraction should be less, and we need higher fiber fraction, obviously, because fiber fraction will define the mechanical properties of the composite. So void fraction should be lower and fiber fraction should be higher. In our laboratory experiment, we will measure these two only. We will measure the void fraction and the fiber fraction from the given specimen.